And we are live. Welcome to another session of our reading group on the Assumptions of Physics project. And today we're going to finish the part about logic and look at the part on experimental verifiability. So let me share the link. There you go. And share the text. I believe we finished this section here, and we were here.
Okay, so then if we agree, then I will start with this paragraph.
Yeah.
Yes. It should be noted that statement narrowness captures more than just the idea of one statement being more specific than another. Consider this harp seal is white and this harp seal is less than 1 year old. Since harp cows have white fur only for the first month, the first one can never be true while the second is not. Therefore, this harp seal is white is narrower statement, is narrower than this harp seal is less than 1 year old. By the same token, we also have highlighted the fuse, which is narrower than the bomb will go off. That is, narrowness can also capture causal relationships, which is essential if we want to develop a basic theory of scientific investigation. So now we have a footnote 9. We considered using the term implication directly, but it seems that it leads to confusion. Implication in classical logic is something different. It is simply another truth function. Moreover, saying that an impossibility is narrower than all other statements sounds better than saying that an impossibility implies all other statements.
Sorry, got
Yes,
distracted from the chat. There you go.
Intuitively, a statement is narrower than another if it provides at least as much or more information when true. If we experimentally verified the narrower statement, then we already know that the broader one is also verified.
It should also be noted that independence is not transitive and pairwise independence is not sufficient. Consider the following statements for an ideal gas. 1, the pressure is 101 plus or minus 1 kilopascal. 2, the volume is 1 plus or minus 0.1 cubic meters. And 3, the temperature is 293 plus or minus 1 degree Kelvin. Since these three quantities are linked by the equation of state PV equals nRT, any two statements are independent, but the three together aren't. This notion of independence is similar, and in fact related, to the statistical independence and linear independence. I think I'll say the next paragraph, I guess, since that was short. We finished this section by showing how every logical dependence among statements can be naturally expressed in terms of negation, conjunction, and disjunction. Consider the statement S equals the sauce is sweet and sour, or it is neither. This depends on the two statements S1, the sauce is sweet, and S2, the sauce is sour, defined before. If we know whether S1 and S2 are true, we can tell whether S is true as well. The idea that we can express the dependence as all possible assignments for S1 and S2 that make the sorry, my brain's taking a year. The idea is that we can express the dependence as all possible assignments for S1 and S2 that make this result true. For example, S will be true if the sauce is sweet and sour, or if it is not sweet and not sour. That is, we have S1 and S2, or not S1 and not S2. Similarly, the statement "the sauce is not sweet and sour" can be expressed as S1 and not S2, or not S1 and S2, or not S1 and not S2, since it is going to be true in all cases except the one where the sauce is sweet and sour.
Each of the cases in the conjunction of all independent statements where each one appears only once, negated or not. We call this expression minterms. A function can always be expressed as a disjunction of all the minterms for which the function is true. This is called its disjunctive normal form because it is a canonical way to express the function in terms of disjunctions. So we define for a subset S, let S be a set of statements. A minterm of S is a conjunction where each element appears once and only once, either negated or not. That is, it is a statement M in S that can be written as the conjunction negation to some power A of S
Yes.
and S. So S is a possibility. So it gives us true or false.
A
So
is
it's
a
either
possibility.
negated or not.
So this is a funny notation, but it actually makes sense. So let me go through it. So you say that not to the true of S is equal to S, and not to the false of S is equal not S. Okay? So if this not true is true, then S is true, and if this not false S is true, then not S is true. So now, if you do this minterms by taking not to the A of S, S, this assignment becomes the assignment in which M is true. Because if M is true, not A of S has to be true. So S has to be true or false depending on whether A of S is true or false.
Mhm.
Okay, so basically M is true if and only if A0 of M is true if and only if A0 of S equal A of S for all S. So it
Mhm.
picks out the assignment. And so this is where if I had pictures, if I had somebody that made more pictures, that it would be a lot easier. Actually, I think, like if you guys want, I think I can go back and find a slide in which I have a minterm a little bit better explained so that you can see the table essentially. And yeah, why don't I do that while Tobias, you read this, and in the meantime, I'll go and look for that
Just
older slide.
okay. So we wrote this as a conjunction of S or not S for a given possibility A, where negation to the true is just or no negation, and negation to the false is negation, basically. In this notation, in a given A0 for a given possibility, we have A0 of M is true if and only if A0 matches A for all statements in S. Okay. Should I continue? We go back to this or?
Yeah, you can continue. I found, now I have to understand how to share it. But, okay, let me get this set up so that, can I remove this? It's one of those, there you go. I don't know, maybe I can even do this. Let me see. Okay, so if I do this now, share this screen, there you go. So the idea is that you have three statements here, S1, S2, and S3, right? And these are all the possible mean terms. So not S1 and not S2 and not S2 and not S3, right, represents the case in which all of them are false because M1 is only true in this case. And then you pick another one like M4, not S1 and S2 and S3, then M4 is only going to be true if S2 and S3 are true and S1 is false, right? So it corresponds to this line here. And M4 is true in all of this. So what basically the mean terms do, right, all these mean terms, you can see they make some kind of like a diagonal identity, right, where all these are ones and all the rest are zero. So every mean term picks effectively a line. And then if you have something else, S, right, that depends in some way from S1, S2, and S3, then what you can do is basically say, you pick the lines in which this is true, which is these three lines, and these correspond to M2, correspond to M5, and M7. And so S is true if and only if one of these three, M2, M5, M7, are true, and therefore S must be a disjunction of M2, M5, M7, which you can then express using S1, S2, S3. So basically this is how it works. So any S bar that is a function of however many other statements can only be expressed in this way by doing all this unpacking. And then in principle you can do simplifications in all of this and so on. And this is something that you do in computer science, because in computer science you have Boolean functions. They can be expressed in this disjunctive normal form, and then you can simplify and you can find the minimal set of gates that you need to implement a specific function.
And it's really as simple as, well, a bit like a lookup table. We just, for every possible statement, we just look, is it true or not? And then we make a giant list of like, this one is true, this one is not true.
Yeah.
Okay. Yeah.
And the important thing is that this is going to be the tool later that allows us to get to topologies and sigma algebra. So you get the state of statements, right? And these lines will actually be all the possible cases, and you can pick the possible cases by constructing the mean terms. Right? So this allows essentially to represent each line as a column. Right? So the column picks a line and the line picks a particular column. So you can go from assignment to statements and vice versa, and then seeing a statement, any statement, as a set of other statements of these mean terms. And so if you can imagine that these were the context of like the mass of the electron, right? This would be all the statements about the mass of the electron, and these would be the possible cases that the mass of the electron could be found when you go and find it experimentally. And then these mean terms would be the mass of the electron is exactly this value, and the mass of the electron is exactly this value, picks up a line, and then everything else can be understood as a set of lines.
Sorry, I have a question. So in this Boolean algebra, so here these statements, these atomic or the minimal statements, they have to be assumed to be independent in some sense, or like should we adjust for this narrowness or broadness of statements? Because otherwise, then maybe one truth value of one statement might already result into automatic truth of some other statement. So then we cannot like decompose it. It would not be decomposable. Or
no, in that case, it would just mean that. So suppose that this case is not possible, right? So because these are not independent, so this case here is not possible. Mm-hmm. Then when you try to construct M3, it would be always false. And so M3 would be an impossibility. Mm-hmm. right? So if these statements are contingent, so they can be true, then they would be true in one line. But they could also be impossibilities, and then they would never be true. Yeah. Yeah, so this is a table that should be added to the book as an example. Maybe I'll add it as a to-do and see if at some point when I'm too tired to do anything else, I can add the table. Okay, let's continue. So this is basically the statement that you can write things in the disjunction number form, and this is the proof. But the proof it's like tedious. The picture is a lot more insightful than the proof. The proof is just there to make sure that everything is in place and actually works.
Yeah, I think these rules are also called like De Morgan laws, something like that. This how to say, distribution of conjunction or disjunction from is it not so?
I don't know. I mainly find them, as I said, in computer science more than anywhere else. Like in logic, I've never seen the same construction called anything. But again, I am not a logician, so maybe the logicians have another name for it that I'm not aware.
Okay, so do we continue with 1.2 or?
Yes, let's just jump to 1.2.
Okay. We now focus on those statements that are verifiable. We have a way to experimentally confirm that the statement is true. The main result of this section is that not all functions of verifiable statements are verifiable statements. For example, since a test has to finish in a finite amount of time, we are not going to be able to verify a statement that is the conjunction, a logical end of infinitely many statements. We are also going to group verifiable statements into experimental domains, which represent all the experimental evidence about a scientific subject that can be acquired in an indefinite amount of time. I'll just read this other. The previous section took care of universality and non-contradiction, but the principle of scientific objectivity requires science to be evidence-based. Consider the statements 23 is a prime number. It is immoral to kill a person exclusively for monetary gain, or God is eternal. They deal with abstract concepts that cannot be defined operationally and therefore cannot be experimentally verified conclusively. Again, this does not mean that these concepts are of less significance, just that they cannot be subject of scientific inquiry. And in fact, one may be more interested in them precisely because of their abstract and therefore less transient nature. Maybe just a question. So there were two examples which are, let's say, I know, connected to morality, which I understand, but this 23 is a prime number. So it means that these, how to say, logical conclusions following some rules, it's also not an experiment, or it's a bit different from the other two. So I don't know, like, what does experiment mean then in this case, or cannot mean maybe?
Well, so, to find out whether 23 is a prime number, you don't set up an experiment, you prepare 23, and then you make an, you have a set of axioms that you set up, and then some rules to prove, and then you prove that. Or you can even take 23 as a prime number, quite frankly, as an axiom. I don't know why you would do that, but, So the point is that the proof of mathematical statements is not done, with experimental evidence. You do it with proofs. And so it's a different way to reach conclusion. And so, even the fact, even what the truth means in this case is slightly different, right? The empirical truth is different. It's a different truth than, the logical necessity proof.
Indeed.
So
Okay.
Wait, question from the chat first. Is there technically not a test for 23 is a prime number, like dividing it for every whole number lower than 23 and seeing that the remainder is never zero? Yes, but it's again something that you do computationally. You don't really, you don't put 23 bottles on the table and do something and then you infer to it, right? Okay, think about this. Think about from a mathematician perspective, right? You want to prove the Pythagoras triangle, right? Pythagoras theorem, and then you take you draw a triangle, and then you draw the the squares, and you cut them up, and you show that actually experimentally it works. That wouldn't be a proof for the triangle, right? That would only show that in that particular case you did something and within some uncertainty there was this relationship, right? Proving the Pythagoras theorem is a completely different thing. It's not. And so even the fact that 23 is a prime number, suppose that you made an experimental test of, you have to make an instance of 23, right? But you want to prove not that the particular instance of 23 is a prime number, it's the whole concept of 23 being a prime number, right? So it's, again, it's different. Or another way to saying it, you don't want to use induction to prove mathematical statements, right? You use deduction. And whenever you're doing experimental proofs, you're always using induction. So it's a different technique.
So yeah, I guess I wanted to add to that. And in some sense, when you do an experiment, you're allowed to then do computations to the data you get in order to arrive at a conclusions. For instance, in astrophysics, that's always necessary. Yeah. But with a statement like 23 is prime, the only thing you're doing is computation, like it is just a computation. So in some sense, could you consider 23 as a prime number to be a result of the trivial experiment where you collect no data and then do computations on it?
Yes, yes. It's another way to say it. It's mathematical facts like this would either be certainties or impossibilities. And as you will see, certain impossibilities are connected to the trivial experiment where you always have something that spits out true or something that spits out false. That's exactly right, yeah.
Okay, yeah. And of course, in math, there's also weird things where you can have statements that are either true or false, but no computation can verify it. And I don't know how that fits in, but
yeah. Yeah. So the issue of provability, in some sense, is similar to the question of verifiability experimentally, because there is a whole problem of you need to be able to do it in finite time. But again, the type of things that you're doing are completely different. So the fact that they are finite time, it makes them similar, but yeah.
Okay. So limiting the scope of our discussion to objects and properties that are well defined physically is also not enough. For example, the electron is green, or 1 meter is equal to 5 Kelvin, are not suitable scientific statements as the relationships established are not physically meaningful. Even when the relationship is meaningful, we may still not be able to validate it experimentally. For example, there is no extraterrestrial life, or the mass of the electron is actually 9.109 times 10 to the minus 31 kilograms, are not statements that can be verified in practice. In the first case, we would need to check every corner of the universe and find none, with the closest galaxy like ours, Andromeda, being 2.5 million light years away. In the second case, we will always have uncertainty associated with the measurement, however small. So we have to narrow the scope to those and only those statements which can be verified experimentally. That is, we have to provide an experimental test. A
Repeatable.
Typo there. Repeatable. Oh, sorry. That looks like a C to me instead of an E. A repeatable experimental procedure, i.e., as evidence-based, that anyone, i.e., universal, can in principle execute and obtain consistent results, i.e., non-contradictory. Second, we must guarantee that the test always terminates successfully if and only if the statement is true. This is both the power and the limit of scientific inquiry. It gives us a way to construct a coherent description of the physical world, but is limited to those aspects which can be reliably studied experimentally. Yeah, sorry, I think that like landed on a pixel boundary or something, and the line on
Yeah, I tried to make it a little bit bigger. Like I always have this problem. Like how big should it be? Because the bigger it is, the less text you see, right? So it's
yeah.
okay. So the thing that I want to comment, like this, this problem of the electron is green and 1 meter is equal to 5 calories. This is exactly why I want statements to be complete and not have a grammar, because being able to define a grammar also means defining types, because there are some properties that are only valid on one thing and so on. But finding exactly which properties are valid in which case and which object is actually the whole problem in physics. So then you would basically be saying, well, you can start, doing this layer only if you have figured out, and then you can't do anything anyway. So that's one of the reasons why I want these to be full form sentences, and there is somebody else that tells us, yes, these full form sentences make sense or not. And again, it's much easier to read this sentence and see that it doesn't make sense than to give you a formal framework that defines in every case when sentences make sense or not make sense.
Okay. Yeah. Note that certainty and impossibility are trivially verifiable, since we know a priori that they are true and false respectively. Also note that if we have two statements that are equivalent, having a test that verifies one means we have a test that verifies the other as well. For example, since that animal is a bird is equivalent to that animal has feathers, checking whether the animal has feathers is equivalent to checking whether the animal is a bird. The subtlety here is that the evidence may be indirect, and it is only the relationship between statements, i.e. the theoretical model, that guarantees the validity of the verification. This should not worry us though, because in this strict sense, most experimental data is indirect. It comes from a chain of inductions, e.g. the pulse of light is produced, bounces off a moving target, and changes frequency due to the Doppler effect. The light signal is transduced to an electronic signal, which finally is displayed on the device, and therefore needs a theoretical framework to be properly understood.
So one of the things that I thought I had already put here, but apparently I didn't. For example, this inference that animal is a bird that is correspond to animal with a feather. Again, all these things are context dependent. So this is true for living animals. If you add the dinosaurs, that's not true anymore, right? So again, the what you consider true in one context is different than what you consider true in another context, and so there is always this problem.
Okay. Axiom of verifiability. A verifiable statement is a statement that, if true, can be shown to be so experimentally. Formally, each logical context S contains a set of statements, SV a subset of S, whose elements are said to be verifiable. Moreover, we have the following properties. Every certainty T in S is verifiable. Every impossibility inverse T in S is verifiable. A statement equivalent to a verifiable statement is verifiable. Justification. To give a better justification for this and latter axioms, we introduce the following pseudo-mathematical concepts. As science is evidence-based, for each logical context S, we must have at our disposal a set of experimental tests, which we indicate with E. Each element E in E is a repeatable procedure. It can be restated and stopped at any time, that anybody can execute and will always terminate successfully, terminate unsuccessfully, or never terminate. As the tests must provide evidence, the output of the test must depend on the truth values of the statements. Therefore, we can assume we have a function result, what is it, E cross A of S, which maps to success, failure, or undefined. For a statement S to be verifiable, there must be an experimental test E that succeeds if and only if the statement is true. That is for all A in AS, result of E and A equals success if and only if A of S is true. Certainties and impossibilities can be associated with trivial tests that always terminate successfully or unsuccessfully, respectively. This justifies assuming them to be verifiable. As for equivalence and verifiability, let S1 and S2 in S and suppose S1 is verifiable. This means there is a test E small in E such that the result of E and A is a success if and only if A of S1 is true. Since these statements are equivalent, A of S1 equals true if and only if A of S2 equals true. Therefore, result of E and A is success if and only if A of S2 is true. We are therefore justified to assume S2 is verifiable. Precisely defining experimental tests as procedures will present the same type of problems in defining statements or logical consistency. Therefore, we'll leave them as primary concepts. But as primary concepts, they only complicate the formal framework without adding insights. Therefore, we use them only as part of the justifications for the axioms.
A bit of history. At the beginning, I was trying to put experimental tests in the framework. And then you had to put exactly the same axiom on experimental tests so that then you were going to put on verifiable statements. So at that point, they were doing nothing in the formal framework. You just put the, you put axiom on this just to transfer the same exact statement on these things. Let's just throw this out and just put the axioms on the verifiable statement themselves. So.
Okay. Experimental tests are the second and last building block of our general mathematical theory of experimental science. As with statements, any language, for example, natural, formal, engineering drawings, computer programs, can in principle be used to describe the procedure, which can be arbitrarily complicated. It may require building detectors, gathering large amounts of data, and performing complicated computations. We're not going to care how these procedures are described, just that it is done in a way that allows us to execute the test. As an example, sorry. Trying to formalize a universal language for experimental tests is not only impractical, but also conceptually problematic. To know what we can test experimentally is to know what is physically possible, which is equivalent to knowing the laws of physics, which is what we're trying to construct a framework for. That makes sense. Yeah. As an example, consider a procedure along the lines of 1, find a swan. 2, if it's black, terminate successfully. 3, go to step 1. If a black swan exists, at some point we'll find it and the test will be successful. If a black swan does not exist, then the procedure will never terminate and the result is undefined. This is something anybody can do and will eventually always provide the same result. It is an experimental test. It also terminates successfully if and only if a black swan exists, so the statement black swans exist is verifiable.
Note that in principle, science can also study statements that can be falsified experimentally. But the negation of any of those is a statement that can be verified experimentally. Therefore, we can develop our discourse by focusing only on experimental verifiability, leaving falsifiability as a derived concept. Nothing is lost. So, footnote, mathematically, the spaces of verifiable statements and falsifiable statements are dual to each other. Maybe I continue. In the previous section, we saw that we can combine statements into new statements. How about verifiable statements? Can we always combine verifiable statements into other verifiable statements? Since all true functions can be constructed from the 3 basic Boolean operations, the question becomes, can we construct experimental tests for the negation, conjunction, and disjunction of verifiable statements.
Question from the chat. Does this setup allow for an experimental test to succeed and another to fail when testing the same statement? No. So the idea here is that you have the best possible test for the statement, right? So in principle, so if a test fails when it should succeed, then it's not a statement of that test. So that does not work. The only case where it's I can say that you can have two actual tests is that one terminates successfully and the other one does not terminate, right? But then the one that terminates in more cases, it's better than the second one. And so you pick the one that is better.
Or would I maybe like combine them and make a statistical argument? Maybe I have something where like I have a device that works like 95% of the time. I would just measure it like very often and then statistically make a statement. Like with that level of confidence, I will consider it to be true. And that now should be, if I take enough data, be essentially like perfect with the best possible test.
So there are these two types of tests, right? One, they are just true or false, and they always get stuff right. And then there are experiments on the statistics, right? So first of all, to be able to define the experiment on statistics, you always have to have the true-false things first, because otherwise you build statistics of what, right? So the one that are true or false are easy. They always do what they need to do. The inference from statistics to the actual statement in terms of come si dice, of confidence, right? It's you need to build that machinery there, because technically the statement would not be right. It's the statement on the interval of confidence. It's not the statement on the statement itself. So if the statement is on the interval of the confidence interval, that's again one of those clear-cut true statement, because you say, okay, I gathered this data and I have this much, and it's true that I have gathered this much, and therefore I can make this inference with this confidence. So at the end of the day, it's again, you just need to be careful of what you want to say, and then if you do, you're gonna come back in the framework. Does it make sense?
Yeah.
Okay.
Well, I wonder if that's also a question about experiments which test, let's say some theories might have just, a number of parameters that we have to measure, and then, okay, we measure them in some interval and that's it. But then we can study other systems where the outcome is really statistical. That's the only outcome, let's say. So then, then I don't know what it means to choose the best experiment if what we should be measuring is not outcome of one experiment, but of ensemble of experiments, something like that. So that's also depends on the context, or what do we mean by experiment? So that's additional complication.
Exactly. And that's how you solve it. You basically say, well, there are different contexts, even the same data in different contexts might mean different things, and you just have to go and clarify what you need. So the reason why this is general is because instead of arguing by, okay, we have all these, so all the arguments come from necessity, right? So that's how you solve the problem. So you get the generalized by saying, look, I don't know what you're doing, But if you want me to have some, scientific observation, some scientific fact, well, first of all, you need to be able to define what the fact is, and the fact has to be true or false. Otherwise, what is it that it's completely undefined what you're talking about? And then there has to be a test for that fact. Some of these facts have to be verifiable in the sense that you have to be able to say, show me that these are true and this is the evidence, right? And however you're going to do it, you basically say, I don't care, but you need to give me those things. Right? And so because you argue from necessity, because really, if you don't give me those things, you basically have nothing well defined, then you're guaranteed that any other setup, however complicated you're going to have, you need to be able to reconduce into that, because otherwise you haven't proved the claim with experimental evidence.
Okay, so do we have the last paragraph here? Is that true?
I think we're here, right? The first important result.
Yes. The first important result is that the negation of an experimental test that is successful when the first is not successful, does not necessarily exist. Consider our black swan example. An experimental test for the negation would be a procedure that terminates successfully if black swans do not exist. But the given procedure never finishes in that case. So it is not just a matter of switching success with failure. Because of non-termination, non-successful does not necessarily mean failure. And we have footnotes. In this case, the old adage, absence of evidence is not evidence of absence, applies. Yes. Moreover, it is a result of compatibility theory that some problems are undecidable. They do not allow the construction of an algorithm that always terminates with a correct yes or no answer. So we know that in some cases, this is not actually possible. In the same vein, we are able to confirm experimentally that the mass of this particle is not zero, but not that the mass of this particle is exactly zero, since we always have uncertainty in our measurements of mass. Even if we could continue shrinking the uncertainty arbitrarily, we would ideally need infinite time to shrink it to zero. What this means is that not all answers to the same question can be equally verified. Is the mass of the photon exactly zero? We can either give a precise no or an imprecise, it's within the range. Is there extraterrestrial life? We can either give a precise yes or an imprecise, we haven't found it so far. Note that we are on purpose avoiding induction. It does not play any role in our general mathematical theory of experimental science, since a decision of when and how to apply induction violates the principle of scientific objectivity.
Yeah.
So, sorry, if I could ask for a clarification on induction, just because, at least in my head, I'm just thinking about like induction on the integers, and I'm assuming that you mean something else here.
Yeah, it's the idea of so in deduction you start with something general, you get something specific.
Mm-hmm.
Induction, you start with something specific and you get something general. So, for example, you see, every time, let's see, what would be a good example? Yes, you see that every time that you take something and you let it go false, right? And then you say, when I let things go, they fall, right? And that's and the problem is that induction does not always work, because you can say you would be like, if you take induction to the letter, the more something happens, the more it should be true, right? The more the times that I left things, the more data I have. Right? So suppose you are 10 years old and you wake up and every day from when you're 10 years old you keep waking up each day. Then the inductive conclusion then would be that the more you live, the more chance, the more you should become immortal, because I'm always waking up, and ttherefore there should be a higher chance that I will wake up the next day. And of course, it works the other way. There is I think there is the famous example of what is the turkey. So the turkey, sees the farmer every day, and the farmer takes care of it, gives him food and so on. And so the conclusion of the turkey is that the farmer is always going to take care of me, and at some point the farmer comes and kills the turkey. And so induction has problems. So I don't remember exactly what I meant with this sentence, I have to say. Okay, we are avoiding direction. Oh yes, because we haven't found it so far. So the point should be that you can you don't need to rely on induction on all statements. You can some statements are if you need there exists one case, right? As long as you have found the one case experimentally, there is no induction. You found it and that's it, right? The induction only happens when, as you were trying to say before, for example, we have some statistical inference and we want to say, oh, this happened this many times and so on in these conditions, and then we basically feel justified that the thing is true.
Sorry, is it connected to basically ternary logics with more than two truth values? Because if we have only two values, then okay, negation of one already tells us that the truth is on the other side, on this negate false value. But if we have more than two values, then negate. Let's say if we have A, B, C, then negation of A could mean that either we have B or C, but which one of those two we don't know. So it can be that, like let's say with this one, it can be that it either does not exist or we don't know.
Right, so the ternary logic is on the epistemic axis, right? The thing is going to be true or false. But in the ternary logic, in the epistemic axis, yes, if there is, I found it to be true, I found it to be false, I have no idea. And so the point is that, and this is where also I have pictures, but they're not in the book. I have them on slides. Like you can imagine the column that is true and false, and then the success, undefined, and failure. And so the statement is true only if the statement is verifiable if the true and the verified part are the same. But on the false side, you could still have falsified and undefined. And so when you flip the true and false, you still have the undefined.
Right. I guess this was kind of our discussion already, but I should say this remark. The negation or logical not of a verifiable statement is not necessarily a verifiable statement. Justification. A statement S and S is verifiable if we can find an experiment such that the result of that experiment is on A is a success if and only if A of S is true for all A in the A sub S. This means that for some A in A sub S, we have that, or we may have that A of S is false and the result of E on A is undefined. That is, the test is not guaranteed to terminate if the statement is false. Therefore, we cannot, in general, use the experiment E to construct a statement that terminates whenever S is false. Therefore, we are not justified in general to assume that the negation of a verifiable statement is verifiable. Yeah. All right, I guess I can continue a little, but while this is true in general, we can still test the negation of many verifiable statements. Consider the statement, "This one is black." It allows the following experimental test. 1, look at this one. 2, if it's black, terminate successfully. 3, terminate unsuccessfully. Ah, okay, that's changed. Note that since this test always terminates, well, assuming you can find a swan, we can switch failure to success and vice versa. In this case, we can test the negation and we say the statement is decidable. We can decide experimentally whether it is true or false. It is precisely when and only when the test is guaranteed to terminate that we can test the negation. right. Should I continue or I can, yeah.
Oh, sorry, I just needed a second to unmute. We are definition 1.28. Okay. A falsifiable statement is a statement that, if false, can be shown to be so experimentally. Formally, a statement S is falsifiable if its negation is inside the set of verifiable statements. So it's a verifiable statement. Justification. Note that the informal definition is based on experimentally showing that the statement is false, while the formal definition is based on the falsifiable statement to be the negation of a verifiable one. We have to show they are equivalent. For a statement S to be falsifiable, there must be an experimental test that fails if and only if the statement is false. That is, for all possibilities, the result of my test is equal failure if and only if the statement is true in that possibility. So let E be an experimental test and consider well, the negated test defined as follows. Run test E. If E is unsuccessful, terminate successfully. If E is successful, terminate unsuccessfully. Since E is repeatable and can be executed by anybody, this negation of E is also repeatable and can be executed by anybody. And therefore, we are justified to assume that this test is in our collection of tests. Now let S be a verifiable statement, then we can find a test such that the result is success if and only if the statement is true. We also have that the result of the negated test is failure if and only if the result of the original test is success and the negation is false if and only if the statement is true. Therefore, for all possibilities, the result of the negated test is failure if and only if the negation of S is false, which means the negation of S is falsifiable if and only if S is verifiable. This justifies the definition.
A decidable statement is a statement that can be shown to be either true or false experimentally. Formally, a statement S is decidable if S is if S is in SV and negation of S is in SV. We denote as the subset of SV the set of all decidable statements. Justification. Note that the informal definition is based on experimentally showing that the statement is either true or false, while the formal definition is based on both the decidable statement and its negation to be verifiable. We have to show that they are equivalent. Let S in S be a decidable statement and E in E an experimental test that verifies whether the statement is true or false. That is, result of E and A is a success if and only if A of S is true, and the result of E and A is a failure if and only if A of S is false for all A in AS. Then S is verifiable. We also have result of negated experiment of E and A is a success if and only if A of negation of S is true. Therefore, negation of S is also verifiable. Conversely, let S in S be a verifiable statement such that negation of S is also verifiable. Let E negated in E be the respective experimental tests. We have to be careful as E and negated E may not terminate. Consider the procedure E hat of E and negated defined as follows. Initialize n to 1, run the test e for n seconds. If e is successful, terminate successfully. Run the test e negated for n seconds. If e negated is successful, terminate unsuccessfully. Increment n and go to step 2. The procedure is repeatable and can be executed by anybody. Therefore, e hat of e and e negated belongs to e. Both e and e negated are eventually run an arbitrarily long amount of time. Therefore, result of e hat of e and e negated and of a is an element of set of success and failure. That is, the test will always terminate. We have result of e hat of e and e negated and of a equals success if and only if result of e and a is a success, if and only if a of s is true. We also have a result of e hat of e and e negated and of a is failure, if and only if the result of e negated and a is success, if and only if a of negated s is true, if and only if a of s is false. Therefore, s is decidable. This justifies the definition.
This is a type of math when you're trying to prove something obvious and it takes a lot of time. So let's do this, and I think we might have to stop.
Yes, corollary. Certainties and impossibilities are decidable statements. Proof. Let true in S be a certainty and inversely in S be an impossibility. By, I guess, the previous result, they are verifiable statements.
I think this is the axiom.
The
axiom of verifiability.
Okay.
That tells you that every certainty and every possibility are verifiable.
Okay. So by axiom 127, there are verifiable statements. We also have that certainty is equivalent to negation of impossibility. Therefore, they are decidable by definition.
There you go. Okay, so we didn't even make it to the axioms of verifiability, which I guess we're going to do next time. We'll stop for questions or comments.
So I'm trying to build this picture of this logical picture of what we're doing. So now what I have is that what will be needed for this scientific I don't know objectivity is the logic that is basically a product of this binary logic and ternary logic. Yes. One representing the actual truth value of all possible statements of the universe, and the other is basically our limitation, what can be done practically in a sense. Yes. Yeah. So then yeah, okay. I think that's all I have for now.
Yeah, so you can imagine, right, statements that you don't have an experimental test, so in this other three value logic would be always undefined, right? Is there, some type of existence after death? Undefined. We can't make the experimental test, right?
Yes.
That's it. Or other things like question of morality, right? It's not that there is not even an answer that would be useful in some sense of what you're doing. It's just you can't make an experiment you can't make the test. In fact, sometimes when you do I don't know if you ever heard the sort of the whole behavioralist movement, like the beginning 19th century, of trying to define the sort of emotion and so on by just looking at behavior. So they had animals, and they were trying to define love by how much time one animal would spend with another animal, right? So of course, these are at best they're proxies, and a lot of the time they just don't work. Or the whole idea of the IQ, right? The guy who defined the IQ basically said, well, we need experimental definition, so this is the test that I'm going to do, and it's going to find out intelligence. Well, it just finds how good people are resolving the exercise in your test. So it's yeah.
Yes. So now, well, let's say I take this binary logic, like we know, or since it's Boolean logic, we understand more or less its rules and how this truth value propagates, and then how the proof is constructed with these, chains of statements. Then if we take the ternary logic, I guess it has rules of its own, which are a bit different. And in the end, what will matter is this, like, how to say, if we will need a proof, then we have to construct the proofs based on rules that apply on this, like product logic, kind of.
Yeah.
Yes.
And the standard thing is that what you do in topology is exactly what you need.
Mm-hmm.
So the mathematical tool set of topology, it's actually that. You have on the background things that could be true or false, and then you have these approximations that are the open sets that represents the thing that we can make experimental evidence of.
I just had a quick question about notation because
Yeah.
we call the set of verifiable statements as subscript V. Now decidable as subscript D.
B,
I
yes.
didn't see for falsifiable symbol. Do we use S subscript F for that?
No, we don't have it.
Okay.
Yeah. It's
This is the
basically
symbol
SP
block.
complement, I guess.
Yeah,
No, it's
okay.
not SP complement. No, it's not SP complement. It's not SV. It's the negation of SV.
Yeah. Okay.
Oh, wait. There are a message from the chat. In octopods, which I don't know what octopods are, they tend to operationalize well-being by the amount of time it takes them to respond to a crab. Ah, okay. In their vicinity by trying to eat it. Predator response, I think it was called. Okay, there you go. Yes. Yes. I always find funny these type of things. It's it's the best you can do in some cases, and and it's not that much. Okay, if there is nothing else, we can stop, and I'll see you next week. I don't think I have anything next week. Let me check my schedule. Otherwise, it becomes like last week that I see next week and then I'm not there. Yeah, I currently don't have anything, so I'll be available. So see you next week. Bye.
All right.
Week.
And stream ended.